Okay, we're back here. It's Tuesday, nice snowy day out, and we're going to be continuing our discussion of heat capacity and latent heat. So I thought I would go outside and get a pan of snow. Okay, so here's a pan full of snow, and I'm going to stick the thermometer in it and let the temperature stabilize for a little bit. And here's a thermometer. This has an offset of a couple degrees. It's off by a couple degrees. And so when I put the thermometer into the snow bath here, and we can add a little bit of water to remove some of the air pockets a little bit. Okay. Let the temperature stabilize for a little bit, and it should read pretty close to zero. There's a little bit of an offset in this thermometer. So now what I'm going to do is I am going to turn on the burner here, and we're going to supply some energy to the ice. Okay. So I turned on the burner, and we're going to watch the thermometer. And keep in mind, again, there's a little bit of an offset here. The temperature is actually very close to zero because that is the freezing point of water. And so when you mix some water and some ice into a little slurry, you get a temperature of around zero. So we're at the freezing point. Okay. So now I'm supplying some energy here to the ice. And let's watch the thermometer during the process here. So temperature is not going up. Okay, so where is the energy going? Well, it's going somewhere, but it's not going into raising the temperature. See, the temperature is staying pretty rock solid. Remember this offset, it's actually close to zero. This thermometer's got a bit of an offset. Okay, so let's watch it. Starting to get a little, the ice is starting to melt a little bit. Don't want to move my camera, so you'll have to take my word. But the temperature's still not going up. Even give it more heat. Okay, so energy has to be going somewhere. Ice is starting to melt. Okay, so go get your coffee if you want. It's going to be a minute. Ice is continuing to melt. So now we have some ice and we have some water. We have some liquid water in there. But the temperature is staying constant. It's close to zero. Again, remembering that there's a little positive offset here in this thermometer. So it seems like none of the energy from the burner, none of this heat is going into raising the temperature. It must all be going into melting the ice. And so, in other words, what's going on now is all of this energy is used to change the phase of ice from the solid phase, which is ice, to the liquid phase, which is water. Okay, still no temperature rise. Ice is continuing to melt. Okay, so it's taken a lot of energy. See, we've had this burner on for a few minutes on high. A lot of energy, and none of it's going into raising the temperature of the water. It's just all going into changing the phase from the solid phase, which is ice. Well, actually, snow has a little bit of liquid water in there, to the liquid phase. Let me stick this back in here, and let me mix this around a little bit. Okay. Sorry about that. Okay, so now almost all the ice is melted. And now the temperature's starting to go up. See how fast it's going up now? So once the ice was melted and it became liquid, the temperature shot up rapidly. So it didn't take much energy to start raising the temperature once we melted the water. Okay, we're up to 30 degrees Celsius already. It changes a little bit because no matter if you place, there's some small temperature gradients, and I drank coffee, and so the probe is moving a little bit in the water. But see how fast the temperature is going up now? That we're up to 35 already. So it took a lot more energy to change the phase, to melt the ice, than it did to raise the temperature. Okay. So I'll continue to leave the probe in here. We're up to 43 degrees, 44, 45. So keep your eye on the thermometer here. 46. But it takes a lot less energy to change the temperature of the water than it does to change its phase. So continue to watch. We're at like 55 degrees here, 56, 57. Wonder what's going to happen. Yeah, we're starting to get a little bit of vapor here, so we're starting to get a little bit of evaporation. So a little bit of the energy is going into evaporation. There's molecules that have enough energy to escape, but there's some that are also coming back. Okay, we're at 69 degrees. Doesn't take much energy to heat water up, does it, compared to changing the phase? 73, 74. Little bit of boiling going on here. We're getting close. '83. Temperature's shooting up. See, it took less energy to change it from 0 to 87 degrees than it did to melt it. We're at 90, 91, 92, 93. Okay. 94, 95. I burned my hand. 96, 97, 98. Wow. Okay, we're up to 98 degrees. So now we're boiling. Water's boiling. So what's going on here? Okay, we're evaporating some of the water. It's going from the liquid phase to the gas phase. Okay. So look at now, the temperature's not going up anymore. It's staying at about 98 degrees. Remember how quickly it went up from 0 to 98? Well, it turns out that at the altitude of Boone, which is about 1,000 meters, my house is about 1,000 meters, a little over, that the boiling point is about 97 degrees Celsius. That's the boiling point of water at this altitude. And remember, this thing reads a little bit high, so it's really probably closer to 97. But now our temperature's not going up anymore. So remember how quickly it went up from 0 to 98? Now it's not changing. It's staying constant, but it's boiling vigorously. So where's all the energy going now? Well, all of this heat now, burnt my hand again. All of this heat again is right now must be going into evaporating the water. So in other words, the energy is going into changing the phase from liquid to gas. Keep watching. Okay. Really boiling now, but the temperature's not going up at all. It's just all going into evaporating the water. Okay. And we could continue. I could sit in here until all the water is boiled and we could just have fun, but I think you get the point now. So once we reach the boiling point, the temperature will not go up until all of the water has evaporated into the steam phase. And it's taken a lot of energy here. See, we're heating this thing, and the temperature still isn't going up. So it's all going into evaporating the water. And this is what's called latent heat. And in other words, if I stick my hand right here, right, that heat, it's gonna hurt, right? I'm going to absorb that. So all of this latent heat is stored in the gas. Okay. So this is an example of latent heat. Latent heat is the energy or the heat that a system absorbs. Okay, we're continuing our discussion of specific heat and of heat and phase changes, and then we're going to go into calorimetry. So let's move on here. So we just finished the demo of latent heat where I heated up the ice into liquid water and then ultimately to steam. Let's discuss what happened here. So we saw in the demo that it took a lot of energy to melt the ice, right? And so if this is a plot here, here's temperature on the vertical axis, and this is the energy added. So basically, it's the amount of heat that was added to the water. And we saw at the beginning that when we first melted the water, it took a lot of energy to change the phase of the water from a solid phase to the liquid phase. Right here. So if we're heating it, start at 0 degrees, we can keep adding heat and the temperature did not change at all, okay? Then once all of the water melted, the temperature went up pretty rapidly. And so the amount of heat that needed to be added to take the temperature from 0 to the boiling point was not that much, right? The temperature all of the energy went into raising the temperature. Then it got up to the boiling point, okay, and the boiling point at our altitude was 97 degrees Celsius, this is sea level. And then all of the energy, if you keep adding more and more and more heat, it all went into boiling the water. So the temperature stayed constant. And in fact, had we continued to boil the water, the temperature would have remained constant at 97 degrees Celsius, because we're at a higher altitude than sea level, until all of the water had been boiled. Now you have steam, and then the temperature continues to go up. And so if you look, you have to add a lot of heat to boil the water, a lot more than you do to raise its temperature. And so that energy goes into the latent heat. It's stored in the vapor. And if any of you ever had a steam burn, what happens with a steam burn is if you get some of that hot vapor on your skin, all of that energy that went into evaporating that water will go into cooling the water. So all the water basically, it will change from steam to the liquid phase, and all of that latent heat will be absorbed by the skin and you'll get a steam burn. And that's why steam burns are very painful, because there's a lot of energy that was stored in this gas as latent heat, and all of that energy gets given back. So this curve can go the opposite direction. If we lose heat, we have to lose a lot of heat for it to cool, and so all of that heat goes into condensing the vapor into a liquid, and that heat is absorbed by your skin and you get burned. And that's why steam burns are so bad. So the take-home points of here is that during a phase change, the temperature stays constant until the entire substance changes phase. And we saw that with our demo, both in evaporating and going from liquid to gas, and in melting and going from solid to liquid. The temperature did not change until all of the substance changes its phase. We saw that much more energy is required to change the phase than it is to raise the temperature. And we can trace the curve if we were to go backwards and we were, instead of adding heat to a substance, removing, we would go in the opposite direction. So here you take a gas and you cool it down to the boiling point, and at that point you would tend to get a transitions. All of the energy would go into condensing into the liquid phase, and then the gas would cool from the boiling point down to 0, and then all of the energy, the heat that's released, would be lost, and
liquid would change to the solid phase. So we can trace the curve in each direction. So one example of latent heat that we'll get into a little bit is weather. Might as well just get into it now. So the energy that's used to evaporate the water, so if you have a lot of moisture, what happens during the day is the sun heats this up, and this raises the temperature, and you start to get some evaporation. And so that latent heat, all of that energy that goes into evaporating the water, now you've got liquid water, you have water vapor, okay? And that water vapor, less dense than its surroundings, begins to rise. It rises and cools. Now it gives back its latent heat because it will cool and it condenses, and it forms clouds. And so you get cloud formation in part due to the latent heat, basically from evaporating the water at the surface, and that energy is given back when it condenses, and you get clouds. So how do we calculate the amount of heat needed to evaporate something or to change its phase? Well, basically, you multiply the mass of the substance in kilograms, and instead of the heat capacity, now we have something called the latent heat. And the latent heat of fusion is the amount of energy needed to change the phase to melt 1 kilogram of a substance. And the latent heat of vaporization is the amount of energy needed, the amount of heat that needs to be added to evaporate 1 kilogram of a substance. And so the latent heat is the amount of energy or heat that needed to be added or removed to change 1 kilogram of the substance, the phase, completely. So here's some examples. For water, it takes 3.35 times 10 to the 5 joules to evaporate 1 kilogram, to melt 1 kilogram of water. That's the latent heat of fusion. It takes 2.26 times 10 to the 6 joules to vaporize 1 kilogram of water. And so it takes a lot of energy to change the phase. And if we look, it takes more energy to evaporate than it does to melt. And that's because you're breaking the bonds of these water molecules completely in changing from the liquid phase to the gas phase. So it takes more energy to vaporize something than it does to melt something. So let's go through an example here of how to combine specific heat with latent heat. So in this example, we're given that for ice, the specific heat is 2,090 joules per kilogram per degree Celsius. So what that means is it takes 2,090 joules to heat 1 kilogram of ice by 1 degree Celsius. Now in the water phase, it takes about twice as much energy. Specific heat of water is 4,186 joules per kilogram per Celsius. And then as we get to steam, when the water is a vapor, it takes 2,010 joules to increase the temperature of vapor, 1 kilogram by 1 degree C. And we're also given the latent heats of fusion and the vaporization. And so the question is, how much energy in part A would it take to convert 1 kilogram of ice at negative 10 degrees Celsius to liquid water at 10 degrees Celsius? Okay, so let's stop your video and try to see if you can work this out. We'll worry about part B in a minute. Let's try part A. All right, so you're back. So to convert ice at 10 degrees Celsius, we need to, first of all, take it to 0 degrees Celsius. So we need to raise the temperature from negative 10 to 0. Then in the second stage, we need to melt all of the ice at 0 degrees Celsius to create the liquid at 10 degrees Celsius. And once the ice is all melted, step 3 is we need to raise its temperature from 0 degrees to 10 degrees. And so in this picture, it's the 3 steps. You need to heat the ice to get it to 0. Then at 0, all of the energy goes into melting it. That's phase 2. And then the third step is we need to raise the temperature, in this case to 10 degrees Celsius. So it's a 3-step process. So to go from negative 10 degrees to 0, we take the mass, 1 kilogram, and we multiply it by the specific heat of ice, 2,090 joules to raise each kilogram by 1 degree Celsius. And then the change in the temperature is final minus initial, it's plus 10 degrees. And we multiply these 3 together. It takes 2.1 times 10 to the 4 joules to convert ice at negative 10 degrees Celsius to ice at 0 degrees Celsius. Okay, that's Q1. The second step is we need to melt all of this ice. And so melting implies latent heat of fusion. So we take 1 kilogram, and it takes 3.35 times 10 to the 5 joules to melt each kilogram. And so you get 3.35 times 10 to the 5 joules, or I took that to 2 seg figs. That's the amount of energy needed to melt the ice. And if you notice, it's much more than it is to raise its temperature by 10 degrees. Okay, now that's Q2. Now when it's at 0, now we've got water at 0 degrees Celsius. The final step is we need to heat it up to 10 degrees Celsius starting at 0. So now we take our mass, 1 kilogram. The substance is now liquid water, so we multiply by the heat capacity of liquid water, 4186 joules per kilogram per degree C, and we're increasing by 10 degrees C, so delta C is 10 degrees, and it takes 4.2 times 10 to the 4 joules to take the liquid water from 0 degrees to 10 degrees. So the total heat is just the sum of each of the 3 heats, and when we add these all up, it's 2.6 times 10 to the 6 joules of heat that's needed to take ice at negative 10 degrees and convert it into liquid at positive 10 degrees Celsius. And if you notice, almost all of the energy that it took was to melt it, okay? Very little was needed to heat the water or heat the ice as compared to the amount needed to melt it. Okay, so that's part A. Now in part B, let's calculate how much heat we would need to add to take that same kilogram of liquid water, and let's start at plus 20 degrees C, and we want to convert it fully to steam at 110 degrees C. Okay, well, it's the same process here. First of all, we need to take the same. So we start at 20 degrees and we go to 100 degrees Celsius, and so delta T is 80 degrees. We multiply that by the heat capacity of water times the mass. Then we take, instead of the heat of fusion, Q2 is the heat of vaporization, and then that's the amount of energy needed to fully evaporate it, and then Q3 is just raising it for 100 degrees to 110 degrees Celsius, and when you add these 3 all up, it's 2.6 times 10 to the 6 joules. So we'll go through this on Monday in lecture if you want to, but I'm assuming that you can follow the same process we did in part A. One mistake I just made before, in the process of going from minus 10 degrees to 10 degrees, I meant Q2. The Q is actually, the sum is 4.0 times 10 to the 5 joules. It's the heat of fusion to melt plus the sum of the two heats and raising its temperature. And so this is what I was referring to in part A. And then part B is if you did the same calculations and started at 20 degrees Celsius, the total energy needed to go to steam when you add them all up is 2.6 times 10 to the 6 joules. And I encourage you to work out this example on your own part B, and then we can go over it in the in-person on Monday if you like. But in each case, almost all of the energy that was required, almost all of the heat, was the heat needed to change the phase. It takes much more than to change the temperature. So here's a thought exercise. Suppose that you are cooking spaghetti for dinner, and the instructions say boil the pasta in water for 10 minutes. Okay. So to cook the spaghetti in an open pot with the least amount of energy, should you turn up the burner to its fullest so the water vigorously boils, or should you turn down the burner so the water barely boils? Okay. So some of us are impatient. We think by turning the burner to its fullest so it vigorously boils that will cause the pasta to boil more quickly, but it turns out it really doesn't help, okay? Because the temperature of water, whether it boils vigorously or barely boils, the temperature of water is still at the boiling point of water, and so vigorously boiling the pasta is not going to help it cook any more quickly than barely boiling. So you might as well just save a little bit of energy and barely boil the water. So now you've learned another little tidbit where you can impress your friends at the bar. So here was the example we talked about before with evaporation, where the energy that was used to evaporate the water was given back when the water condensed to form clouds. And this energy is given back here as in the form of latent heat. So the final topic that we're going to get into today is something you're going to cover in lab in the next week. And this is called calorimetry. And you might have already done this if you've taken a chemistry class. So calorimetry is an experimental method for determining heats of reaction and the specific heats of substances. And in your physics lab, you're going to use this to determine the specific heat of a metal. Okay, so what you do here is you weigh a substance of a mass, and so we know the mass of the substance, and you heat the mass up to some known temperature, and then we stick it in this water bath here, and you have a hot substance, and you have a cooler water, and the energy so you have a hot body and a cooler body, and then you have a cup here, a calorimeter, and this is completely insulated, so that in principle no heat can enter or leave. And our system here is the cup, the water, and the sample. And so no heat can enter or leave the system, and so whatever heat is lost by the hotter body, which is the sample, is gained by the water in the cup. And so what we're going to do is if we find the equilibrium temperature, and so the water will end up at some temperature that was warmer than what it started at because it will gain some of the energy lost by the solid here. And if we know the initial temperature of the solid and all of the masses, the mass of the water, the mass of the cup, the mass of the solid, and we know the final temperature, we can get the specific heat of this substance that the solid is made out of. Okay. So what we do then is, since no heat is added, and if Q1, Q2, and Q3 are the heat added to the cup the water, the sample, anything else in there, Q net is 0. In other words, if some of these are positive, meaning they're gaining heat, the others must be negative, meaning they're losing heat, so that because there's no net transfer through the styrofoam. So let's do an example here, and this is pretty similar to what you'll be doing in lab, so you can use this example to help with your pre-lab. So suppose we have a water calorimeter, and we want to measure the specific heat of some alloy. So we weigh the alloy, and the alloy is 150 grams, so that's the mass of the alloy. And we heat the alloy up to 540 degrees Celsius. So we heat it, it's pretty hot. Then we're going to stick it in a cup of water, which is 400 grams of water, and that water is in a 200-gram aluminum cup. Okay, and we measure the so now we know the masses of all three: the cup, the water, and the alloy. And we know we can measure that the temperature of the water in the cup is initially at 10 degrees Celsius. Okay, that's the temperature of the cup and the water, and the alloy is heated up to 540. So you stick the alloy in, and you let all of them come to some final equilibrium temperature, which we're going to measure. And the final temperature is 30.5 degrees Celsius. Okay, so it ends up at a higher temperature than the water started at, and a much lower temperature than the alloy started with. So now we know all the initial and final temperatures, and we know the mass. And so what we want to do is based on this, we're going to find the specific heat of the alloy. Okay, so as a hint, the heat that's lost by the alloy in cooling it is going to be the heat gained by the cup plus the heat gained by the water. Okay, so in other words, the heat added to the alloy plus the heat added to the water plus the heat added to the cup, all of them have to be 0 because they're all contained in this insulating material, so no heat can enter or leave. So whatever is lost by the alloy, this will be a negative number, will be gained by the water and the cup, which will be positive numbers. And so they all have to add up to be 0 because no heat could enter or leave the system. Okay, so the next step that we do is we can write down that the heat that's lost by the alloy is the mass of the alloy times the specific heat of the alloy. That should be an A, I'm sorry, that's a typo. Times the final temperature, and they're all at the same final temperature. So for T final, we can just put T for all of them. So the change in the temperature of the alloy is T final minus the initial alloy temperature. Okay? The heat changed by the heat that's added to the water is the mass of the water times the specific heat of the water times the temperature change, T final, which again is the same as the other two, so we don't need to add subscripts, minus T water, the initial temperature of the water, and then the heat added to the cup is the mass of the cup times the specific heat of the cup times the cup's change in temperature, which is final temperature minus the initial temperature of the cup. And all three of these have to add up to be 0 because no heat can enter or leave the system. Okay? Now we know that the initial temperature of the water and the cup are the same. So we can rewrite this as T water. We can factor these out. And all we did is a little bit of algebra here. And we know the initial temperature of the water and cup. We know the final temperature. We know the specific heat of the cup. We know the mass of the cup. We know specific heat of water. We know the mass of the water. We know everything but the specific heat of the alloy. In other words, we know all the other specific heats. We know we've measured all the masses, cup, water, and alloy, and we know the initial and final temperatures of all of them. So we can solve this algebraically for the heat capacity of the alloy. And when we do that and we plug in all of these numbers, we get that the heat capacity of the alloy is the specific heat, is 500 joules per kilogram per degree Celsius. And so this technique is called calorimetry. And it just uses the fact that if no heat can enter or leave this system, if we enclose it in an insulating cup and we heat up the alloy, the heat that's lost by the alloy is gained by the water and gained by the cup. And so we can write this mathematically as Q alloy plus Q water plus Q cup is 0. We write each heat added in terms of the temperature changes in specific heats. And if we know all of the masses and all of the temperatures, and if we know the specific heats of the cup and the water, we can solve this mathematical equation to get the specific heat of the alloy. And this is what you'll be doing in lab. Most likely, I think it's next week you're doing this. So that pretty much is it. There's other worked examples I put in here for you. I encourage you to work these out, and we can go over these in Monday's lecture. Another example here with heat removal in a jogger, which is interesting if some of you, I'm sure, run and work out. This is a good example. So we will go over each of these in person on Monday, if you would like. So that's pretty much it. So have a good day and enjoy the snow.